Today, I'd like to talk a little bit about um, the notation that I recently introduced um, in um, in service of helping people to understand the algorithm that we've been talking about to reconcile finalization with block merge. And just to give a little bit of background on that, and how it can be extended, and sort of the purpose and function, and in particular relating it to notions of knowledge and learning. So let me just bring up the little draft. Okay, can everyone see the screen?
Yes.
Yes.
Hopefully that's a little clearer. The basic idea is that we use the turnstile symbol, and to the left we're going to put the identity of the validator, which you could think of as the signature of the validator, which identifies it from all the other validators. We'll put the block that the validator has published at some given height, and then we will put its immediate justifications. So does that make sense to folks, people here? Frank, I know you haven't been around for a while, so does that notation make some sense?
No, yeah.
Cool. All right. So I remember, so people who are familiar with logic or type theory are familiar with the use of this turnstile notation as basically providing a notion of a typing context, or a judgment in which the things to the left of the turnstile are close up the or pieces of information that are necessary to close up the stuff on the right of the turnstile. So, for example, one can represent the situation prior to abstraction. So if you have if you have that given some variable x, you can form a term that uses x with get that it's of a given type. Then when you can abstract over that term and get the abstraction is an arrow from the type that you closed up over to the type of the term. To make that a little bit more concrete, I'll just put that down here in the bottom so that we can, just as a little scratch pad so that we can see what I'm saying. So if I know that if under the assumption that x is of type t, then I can, if given that assumption, I can determine that some expression, say e, is of type t prime. Then I can conclude that if I get rid of the x on the left-hand side, so just so that we're clear, let's say I've got some type, say, of course, it doesn't do. All right, let's go this way. All right, so suppose I have a bigger context, and part of it is X, and the rest of it is gamma. Then and using that, using all of this contextual information, but in particular singled out from that contextual information, I have picked that X is of type T, and E is some expression that uses X. And with this context, I can conclude that instead of using T prime, let's use U. I can conclude that E is of type U. Well, that would allow me to conclude that, grab the symbol. Oh, I can do that the other way. That lambda X dot E is of type T. Oops. Given gamma. So here I've gotten rid of the X, right? The X is here. And I've moved the T from decorating the X to indicating the type of things that we might put in the position of X. So that's one of the ways that this turnstile is used. So those of you who are familiar with type theory or typing in programming languages, you'll be familiar with this kind of usage. It's also through Curry-Howard, we find this kind of symbol used in logical settings. So you can imagine that really this kind of thing decomposes into all the term formation stuff and all the type formation stuff, right? So there are really, you know, if we colored this, right, we can say, how about we color these, say blue, and we color these, say red. Then we can see that these kinds of notations are really blending two different things, and that's really the essence of Curry-Howard. So this is blue, and this is red. And so really what's going on, if you would allow me, is we've got a blue system and remember this, we'd get rid of all the red information, the gamma, so I'll just make it the blue gamma. It's only the blue part of gamma. And the red information goes away. So we've got this kind of formation, but we also have this kind of formation. So we get rid of the blue stuff. So we'd only take the red part of gamma. Get rid of all the blue stuff. So it's the red gamma. And you can kind of see this is telling me how I can form terms, right, independent of their types, so legal terms. And this is telling me about legal formulae or legal types. And in judgments like these, we're seeing the blending of the two all into one notation. Let me just stop there and check and see if that makes sense to folks.
So if we separate these two, blue and the red, they basically means the same, right?
Well, this doesn't have the red information in it.
I mean, if we see them separately but together, are they completely the same as the?
Oh, you'd have to say how they're connected. It's not clear immediately that you need to put the T with the X, for example.
I see.
Right. So this says how they're connected.
I see.
So, any other questions? Okay. All right. Good. So then, the point of introducing notation like this up here. Oops. Where did it go? Here we go. Let me grab this one. Is to indicate that there's something going on that's similar, although not exactly the same. We could get rid of, under some mild assumptions, like a validator can only produce a single block at a given height, because otherwise they would merge all the blocks at the same height. We can simplify it like that. Does that seem fair? Anyone confused by that idea?
So you said that the V is the validator, and you said that produces the block on some height. Can we also say that this can be blocked from some other validator, but is in the context or seen by this validator? I mean, this the V.
So that's a good one. But what we're saying is that at the point that V is producing the block, this is what it's seeing.
Okay.
Is it necessarily a block height, or can we treat as sequence number?
Sequence number is not clear. What we're saying is that this is the distance from the last finalized block that V has produced.
Distance in terms of this row, so the full row, not if there is direct child, for example, 5.
No. Here
ahead.
Here we're only talking about this notion of height, as opposed to the one you're referring to, which is more subtle. This is just that somewhere in here is a justification that of a block that was produced. So from this notation, we can conclude that there's an I between 1 and n, such that we have
H minus 1.
Minus 1.
Yeah, H minus 1.
Mm-hmm.
Right, and these will all be so if I give this a name, right, so if I call this block, say B, right, then we know that there is an I. So just to make it super clear, we say given, we know that an I, which is between 1 and, let me see if I can make that cleaner. Such that B is equal to J sub I. Does that make sense?
Yes.
V here doesn't refer to some particular sender. It's just some sender.
No, we've been very careful to indicate that this V is producing this block.
Mhm.
Okay. And so in this case, this V is producing this block.
Yeah, this what makes me confusing, because if we're saying that H is this height, not the next block, which can probably be several heights above, then this
No, it
H
can't be
minus
several
1.
heights above. It cannot be. That's the I'm giving you definitions here, not calculations.
So it's
So just to be clear then, let's assume. So we assume that let's say F1 through K are the last finalized blocks. Friends, you know what I mean. Okay.
Mhm.
All right. So now, so therefore, V has produced one of them.
Mhm.
Okay. Since they are finalized, we do not have to look at their justifications. It's as if they were Genesis. So we can write V, let's say Fi. Okay.
Mhm.
Okay.
Okay, FV maybe better, because it's
I understand. I'm trying to keep the
okay. Mhm.
Oh, okay. So we have V thinks that Fi. And I don't have to put in the justifications. Okay. And in particular, so that's at height 0, right? So then we would have, or so to be completely, to be consistent with the line above, we have 1 based counting.
Could you scroll?
That's going to be a little bit
down.
tricky. So the counting will be 1 off. So hopefully you'll be okay.
I mean, could you scroll down a bit? It's going off the screen.
Sure.
Okay, thanks.
Okay. So just to be super clear, right? There will be. Oops. Okay, so Fi will be in there, and then there will be some other J1 through Jn. Okay, so that's the block that V produces after it produced the one that it finalized. Now, in the notation above, this would be called V2, but just so that we're, hopefully you understand my, the
Yeah,
reason.
again.
Okay, all right, cool.
So it's self-link.
Yeah,
So
so then, V would think that, oops, 2. So if I give this name, if I give this a block, say B, right? Then v2 would be b comma j whatever j1 prime j n prime, okay, and so on and so forth. So then height is going to be crystal clear.
Yes. I
Okay.
mean, maybe like Tomislav and I understood this differently. So just to make it clear, it's not a height at the sense that we have now. It's not block height. I agree, Tomislav.
Yeah. Yeah, first I was thinking that Greg is talking about block height, but this is the height of each layer where we will see the fringe.
Why we cannot call it sequence number? Is the next, if we're assuming that there's only one block at a particular height, this h, why it's not
But there isn't only one block at a given height, right? There are many blocks.
from the same sender, from one sender?
Sure. The reason I don't like sequence number is because because you have left out the context of who is the block producer. So that's why. Whereas here, the height we know as the height of the defined in terms of this sequence here, right? Or in terms of this chain of events, right? But it doesn't matter, you know, like I don't really care. You know, we could call it Gnorf plaid. It just
Just to understand.
as long as we're right. So in this context, I will call it height. If you want to call it something else, I don't care. But for today's presentation, I will keep it to height.
Sure.
Go ahead, Thomas.
I was just thinking that if we are calling this sequence number, maybe if we want to say that we see the hole and the sequence number cannot have hole, and so maybe, yeah, better not to call it sequence.
Yeah, because you can have holes. Right?
Yeah.
Okay. All right. So
you can so sorry, you can have holes, right?
yes,
So
that's why sequence number is not such a good number.
there might not be a second. There might not be v with the height 2. There might be.
No, there will be. It will always be a v with a height 2. That's my point. My definition means there will always. This is always defined because it's defined in terms of what v is producing and what v sees.
Okay,
not,
I see. Okay.
Not in terms of what everyone else sees. And that's why it's so, this is the whole point of this notation, is to begin to think about what a given validator sees. Not the God's eye view that is given when you're looking at a diagram like this. In many respects, these diagrams are incredibly misleading because diagrams like this are not seen by any given validator until they publish a block that say they have seen the diagram. Does that make sense?
Yes. Basically, if the validator's view is always this validator always see himself as the one who is the first one who sees everyone else in the back.
Something like that. Yeah. So but this is so I remember the first time I heard Lucian Visick, who is a brilliant mathematician and computer scientist, read the symbol as thinks that. So he would say gamma thinks that lambda x dot e is of type T arrow U. Right, so that's a nice reading of that line. Does that make sense?
Yes.
Okay, so we can steal those intuitions and apply them here. And in fact, that's the whole point of introducing this notation. V thinks that at height 1, there is that the block at height 1 is justified by Fi and J1 through Jn. V thinks that at height, the block that it's producing at height 2 is justified by B, which is this one, and J1 prime through Jn prime. So that's the English reading of these symbols. Are we comfortable with that?
Yes.
Yes.
Okay. All right. Good. So now we can do some fun and games. We can say, for example, V1, and I'm going to introduce a symbol. V2 tensor V1, and this is not commutative. Okay, so this is not the same as V2 tensor V1 unless you apply a certain operation. So V2 thinks that H, and now we can put in our justification, say J1 through Jn, and H prime, oops, J1 prime through Jn prime. Now you can see why it's important to keep the order, because the order tells you which is thinking which. Does that make sense?
Yes. Yes.
Okay, good.
So you're not suggesting that V1 and V2 are like combined in some way. You're just making two statements.
I'm combining the two statements into one. In a very,
this doesn't mean that.
yeah, in a very specific way, right? So we're using the order on the left and the order on the right to do the combination in very much the same way that, so we have two statements, right? And there's a way to combine them, right? But notice that there's something different going on here, which is that these two statements, so really all this is a combination of this statement and this statement. Right? So I've combined these two statements into this statement, right? And it's slightly different than the way these two have been combined. Why? Because blue things are at term level and red things are at type level. So we haven't introduced types yet. I can, if we have enough time in today's hour, I might, but we're only doing terms right now. Does that make sense?
Yes.
Okay, good. So, but because of that, we can imagine that we can begin to do formation rules. In particular, we can do a rule like this. Does that make sense now as a rule?
Yes.
Okay, good.
Can I ask you why are you using tensor, not just comma? V1, comma V2.
Because comma doesn't have a meaning of not interacting, but tensor has a meaning of isolated or separated or not interacting.
I see. So when we say gamma, comma, x of type t, this doesn't mean that x of type t has some interaction with gamma.
In this particular context, typically you're not going to get your x is going to show up distinctly, but it's not always the case.
Mhm.
Okay. So so this gives us, and now you can see how these rules correspond to diagram formation, right? So in particular, I can now write down portions of these diagrams. Does that make sense?
Portions. Oh,
What do you mean
so
So for example,
can-
I could write down just this chunk here, the AB chunk, without the rest of the diagram.
mhm. even
Mm,
so you're
even-
ignoring some justifications.
Right.
Mhm. Okay.
even though B4 has justifications from D and E, you're not drawing them.
That's correct. That's correct. And so we can talk about when a subnetwork has some knowledge or a view. We can talk about when an individual, so let me put it in the other way. We can talk about when an individual validator has some knowledge or a view, right? We can do that for many different validators. And now we can talk about when a subnetwork has collective knowledge, but that knowledge is not in the head of any particular validator. It's in the whole network, the whole subnetwork here. But that doesn't mean that V1 knows what the network knows. Does that make sense?
Yes. Yes. Yes.
Okay. So, but we can also say when V1, so in particular, we can now write down statements of the form V1
Mhm.
Vn thinks that, and here we will go H1, and now I'll use matrix notation. Right? So
When I use H here, previously you were using only 1 and 2.
these are numbers, they're heights. So I'm using H as a particular height.
Okay.
Okay. If it helps, I can turn all these subscripts into actual subscripts.
No, I mean, previously in this C's then you were using only digits and then H and H prime.
Well,
So
these
I
are
was
just
saying.
variables ranging over numbers. H
Mhm.
ranges over 1, 2, 3.
Yeah.
Okay. And I just need a bunch of different variables. So rather than,
Mhm.
you know, right, I'll just number the variables, and that makes it easier. Really? You're not going to let me do that? will only let me do them one at a time. Is that really true? What? Oh, wow. Okay, screw that. Well, wow, it won't let me undo that. Okay. Anyway, you know what I mean. I'm not going to try to fix this right now.
Yeah, sure.
Okay, all right. So this then correspond when all of the validators are listed and all of the blocks they have produced, these heights may not be the same, right? H1 might not be the same as HN, for example. This allows me to produce this notation here is a notation for an entire diagram of this form, where this is all of the validators in the bonds map, right? And these are the blocks that they have produced to date. And so there's a value, I think, in this algebraic notation. Notice that it allows me to describe partial diagrams, individual validator views, whole network views, and it is particularly compact. Compare this expression with this diagram. And in particular, it also allows me to do things like, I can now say when validator VI knows what the network knows. How do I do that? Any takers?
I was thinking that maybe if we have a tensor of all, if we have tensor of all the justifications for some block that this validator produced.
Yeah, that's just about right. We just have to say VI thinks that, and now it's going to be so using the same indexing scheme, right? So there's going to be an HI here that corresponds to that, right? So it's going to be HI plus 1. And what does it see? Well, it sees each of these guys. Now, VI knows what the network knows, right? So that's a nice compact notation for talking about states of knowledge. Is that making sense to folks?
Yes.
Okay. Okay. So using this kind of formalism, we can see when the network learns something and when an individual validator learns what the network has learned.
Yeah, well, the only thing that I want to say is that you are assuming here that VI sees all senders, right? So each
No,
I through
no.
N presents
What a particular validator has seen is listed explicitly.
I through N, and this is the whole bonds map.
That's correct. If HI plus 1 does not include one of these, then VI does not see what the network sees. So the question is, what do I have to write down in order to be confident that VI saw what the network saw? This is what I have to write down. Now, there's a relaxed form of, does that make sense, not Sepper? Does that, do you understand?
I think so.
Okay. Now there's a relaxed form. Imagine that, for example, VI sees some H I plus J, which sees some HK, which blah, 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 sees what the network saw, right? So it might not be that it is immediately at hi plus 1 that vi sees what the network saw. Does that make sense?
So
So
in language, it's vi saw messages from all senders. So they're in justification, which means that vi saw view of the whole network because it saw message from each sender.
That's this statement.
Yes.
But it is possible we could write down another statement of the following form. So imagine that at vi plus 1, one of these is missing. Okay, so we'll go, h, let's say k minus 1, and you'll forgive me if I just put ... in here, and hk plus 1, but not hk, k plus 1. So let's say that it's missing hk, right? So there's a hole, right? So in that sense, vi at hi plus 1 doesn't see what the network saw, right? But there could be another block that eventually sees the whole way across. And you could imagine that, in fact, not just one block, but multiple blocks. So maybe at hi plus j, it sees only 2 blocks in addition to the one it produced, right? So I'm just going to leave the convention that I is going to be the block at the ith position is going to be the previous block. Okay, just for now. And then, but let's say that there's only an H1 and an H2 at this I plus j height. But that this one gives it, and for grins, let's make this H2, K2, K plus 2. Okay, so there are 2 blocks missing here. Now we can see that it is possible for this block to have visibility to the first of these, and this block have visibility to the second of these. And so at this point, VI sees what the network saw. Does that make sense?
Yes.
Okay.
So basically, VI needs to go to higher height to be able to see the whole network on some lower height.
Correct. Exactly. And so, all right, it's already 13 minutes until, so now you can see that you can restate all of these conditions in this algebraic format. Does that make sense? So as for fun, what do you have to do to describe holes? And what do you have to do to describe lateness using the algebraic notation? So these are homeworks. If you were going to describe a hole, right? So in our diagrams, we indicate holes. And in our diagrams, we know we have talked about lateness. So the question is, in our algebraic notation, what does the expression or set of expressions or chain of expressions look like that describes a hole? and what does an expression or collection of expressions look like that describes lateness? And you can keep going. What does an expression look like that describes a network partition? So here's a piece of a network. And what does a partition need? Well, a partition needs to be able to say that all of the parties in the partition have seen the lateness of the missing parties. So we know what it means to say when a given validator has seen some condition in the network, something like this, right? So, and we know how to combine those statements. So what does it mean for a subnetwork to be a partition? So can you write down that algebraic expression? Does that make sense?
Mm-hmm. Yes.
Well, it's the tensor of v1, v2, and vn doesn't have some justification.
Yeah.
So vi seen vi through vn, and all of them doesn't see that particular justification. It's below.
Yeah. Well, write it out. It's instructive. It's instructive.
Sure.
It's useful to write it out. And then you can start to see that the algebra is as valuable as the topology. Right. And so, and we have this nice crisp duality between the algebra and the topology. So with the remaining time, let me just indicate a few things. So it's very easy to imagine that we put conditions on things over here. And it's, so what would the conditions look like? So the conditions would look like descriptions of trees, right? So, so you could put over, so now to start to introduce the red, so all of this is blue level, right? Right, and so the question is, can I add red stuff into this notation? And so now one way to add red stuff is to remember that these validators are not really just identifiers. The validators are actually idealized as Erlang programs, right? So what are the Erlang programs? So the Erlang programs are basically little tiny loops, right? They receive certain blocks and they produce certain blocks based upon conditions provided by. So roughly speaking, a validator V, which is parameterized in ports for all the other validators plus its own port, right? So it's going to have, you know, little v1 through little vn, right? So this is a given validator, and some vi is where it's listening for messages, and all of the other v's are j's are where it's sending messages. Does that make sense?
Receiving and sending in the sense of sending a block, the whole blocks.
It's sending blocks, yes, exactly.
Mm-hmm. Okay. Mm-hmm.
Okay, so therefore it's going to look like for block. Where's the block coming from? It's coming from VI, right? So VI is the one that is its identity. You could associate that with its signature. And then what is it going to do? Well, it's going to produce a block right? So it's going to say V J. Let me do it this way, just to be simple. V1, and I'll make it even simpler. Let me do this. And then we do let next block equal, and now we're going to say, we'll just say H, and we can go get the H later. You could sort of, anyway, it doesn't matter. And it's going to produce and the blocks that it has seen. So what are the blocks it has seen? Well, for grins, let's just say that there's some state variable S, right? So these are all the validators, and there's some state variable. And so let's do it this way. And we'll do H and trying to decide whether to break them out or just to do it as a list. Or in the interest of time, I'll just do it as a list. And then, so you know what to do then. Okay, so that's coming from our state variable S. So you could think of S as like the tuple space. Okay. And so now we're going to do H, and then it's not quite the tuple space. It's more like the hot store or something. It's the blocks you've seen. So H, and then we're going to splice in the block list. Right, so like that. And now what we're going to do is on V1, we'll send next block, and then parallel, blah, 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 on VN, and everything but the VI, right? We're not going to send it out on VI, but all the other ones. Next block. And then finally in parallel, we'll go back to being V1 through VN, and we need to have updated the state in some way. So I'll just do S prime in the interest of time, but you get my point.
I mean, we can also send on VI, basically because we are updating its own state.
Sure, you could do that, but the details of this are not particularly important. Let me do this, and then that closes the 4. Okay, so that's roughly the shape of each VI. Does that make sense? People following?
Yes, yes.
Okay, good. So because it's a rolling program, I can now give it a namespace logic type. I can now say V1, VN, S is of a particular type, say T. And this will now describe constraints on the actions here, right? So for example, we could constrain the kinds of blocks that it can see before it proceeds to the next level, right? So I can take all these T's and I can associate them here, right? That makes sense? I can put a colon T1, blah, 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 colon TN. So now I've got red information on the left-hand side. And what sort of red information do I have on the right-hand side? Well, here I can run the OSLF algorithm just on these tree structures, because all these are trees, right? There are trees with you can think of the nodes as labeled with H's, and then the branches go to the next tree. A J11 is a tree, right? So this is a tree, and then it'll have a node which has got an H and blah, 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 blah. And so I can describe trees in a nice data type, and then I use OSLF on that data type, and I get a similar kind of type system. And then I need to be able to put those types in a tensor. So I have to also have tensoring capabilities in the type system. So in the interest of, I've only got 1 minute. I can't spell out what the tree types look like, but they're really quite straightforward. I can get to them next time. But essentially you have tree types over here that are consistent with behavioral types for these programs. In other words, there's only certain kinds of trees that will be allowed given the behaviors of these validators. Does that make sense?
Yes.
And so that is how you add the red information to these statements.
And when you say V1 of type T, this is not just like usual structural type. You basically described how this validator can
proceed.
make transition or
yeah, exactly.
Like,
the kinds of COM rules it's allowed to run.
And in this case, this is very simple COM rule, which means I have a list of blocks, and I will just add one more.
For example, right?
Yeah. Yeah, that's nice.
Cool. So the point is that all of this stuff that we've done here not only simplifies in some sense these diagrams, but it now connects it back to standard notation over here and to the behavioral types, right? So we can now check that our diagrams fit within typing constraints that we impose on these kinds of statements. So we can now talk about a way of approving Casper correct, because we now have all the pieces of information that we need in order to say that for the Casper rules, which we have up here, for example, they correspond to the formations of certain kinds of diagrams that are used by validators that have these kinds of behaviors. Does that make sense?
Yes, yes. And
So this is how to do a compact correctness, a formalized correctness proof for this version of Casper.
And if we have this tensor type, we can describe exactly what when the network see equivocation or like wrong type.
For example, yes, you can describe equivocation, you can describe lateness, you can describe holes, all the properties necessary in order to formalize Casper are describable within this framework, both at the term level and at the type level. Merry Christmas.
Yeah, thanks,
All right.
Greg. Good discussion.
Yeah, I'll see you guys in the
That's very nice.
Thank you.
in the Dev stand-up. Cheers.
Right.